So hey guys, I'm totally not here today. Went scuba diving over the weekend with my son. It was so much fun, but now I'm sick and just need a day. So I'm in my pajamas in my bed making you this video. First, I thought I'd show you a couple pictures from our trip. The picture on the left was from the Comal River in New Braunfels, Texas, and that's where we did our first 2 certification dives on Saturday. Yes, my son is taller than me, and that went really well, except the water was really muddy and it was hard to see. On Sunday, yesterday, we dove in Aquarina Springs over by Texas State University in San Marcos, and that's the picture on the right. The water was super clear. We could see all the way down to the bottom, and there was a cannon under there and all kinds of fish, and it was pretty cool. So technically, I'm a certified scuba diver after yesterday. So it was really fun, but I got really sick. It was cold out. So you should have out a piece of loose leaf paper, and couldn't tell you what page number we're on. I believe our purple electronegativity chart was 73. So your loose leaf piece of paper needs to say Ionic Bonds on top, and it should have a page 74 in the corner. And here's my joke of the day. The name's Bond, Ionic Bond, taken, not shared. Because if you remember, when we say that electrons are taken, we're saying somebody gives them up and becomes positive, and somebody else takes them and becomes negative. So last week we said that an ionic bond was a transfer of electrons. So real quick recap. Ionic bonds, transfer of electrons from the metal to the nonmetal. When that happens, the metal becomes positive, the nonmetal becomes negative. We should know opposites attract. We call these electrostatic forces. And because we now have these opposite electrostatic forces, it pulls those two atoms together and makes them stick. One thing you don't know about ionic bonds is that they're very strong bonds. Because of those electrostatic forces, they tend to be very, very strong. And because they're very strong, they have high, abbreviate, melting point and high boiling point. So if I gave you an ionic bond, it would be really hard to melt it and be really hard once you melted it to get it to boil. Let's talk about a couple of examples. Salt. Salt is our beautiful example of an ionic bond. How do I know? Because I've got my sodium, which is my metal, giving up his electrons to chlorine, who is my nonmetal. So sodium is going to become my positive charge. Chlorine will become my negative charge, and those opposite charges hold them together. Have you ever tried to melt salt? Well, if you put some in a frying pan on your stove, you're going to be there all day staring at it because you're not going to be successful melting salt. Its melting point is just too high. Another property about ionic compounds is that they are crystalline, which means if you looked at them under a microscope or put them between your fingers, they form these nice little cubic patterns, and they're real gritty under your fingers. If you put some salt grains in your fingers and twirled them around, you could feel the sharp edges on those. So today we're going to talk about how that happens and why that happens and what that looks like. So in our next little section here, which is our last section, we're just going to draw some pictures. And so this little section is called Ionic Bond Diagrams. This is all over the internet. If you don't understand what I'm showing you today, you can find pictures, even some YouTube videos, but they tend to only do the easy examples. They didn't do anything up to quite our level or my standards, which is why I'm making this video. So let's start with our easy example. Let's start with sodium. So here's example 1. We're going to bond sodium and chlorine. So write that in your notes. Example 1, Na plus Cl. So we're going to draw a picture of what's occurring. Sodium down here, you should remember he's in group 1. So because he's in group 1, he's bringing 1 valence electron. So I'm going to pick dots to represent my 1 electron. Then I've got sodium over here. I've got chlorine over here. Chlorine is he's in group 17. So he's bringing 7 valence electrons. I'm going to pick an opposing symbol. I'm going to pick X's because it's easy. 1, 2, 3, 4, 5, 6, 7. Well, we should remember, since sodium is over by Frank, he's got a low electronegativity and a low ionization energy, which means he gives it up easy. Scandalous. And so this electron is going to get given up to chlorine. Because if you notice, chlorine only has 7 valence electrons. He is not stable. So he is close to fluorine. So he has a high electronegativity. So this is that tug of war we were talking about. So chlorine is going to yank sodium's electron away. Sodium didn't really want it anyway. And it's going to place it right here on the outside of chlorine. So that is the actual diagram. Sodium gives up his outer electron, and now he looks like neon. So even though it looks like sodium doesn't have any valence electrons, we know on the inside levels he really has his 8. We just don't draw those. But chlorine now has his 8, so it looks like this. Sodium lost an electron and becomes positive, so that means lost one. Chlorine gained an electron, so we put a negative sign. That means gained 1. This step is called the ions. We're representing the ions, so I want to see this step. So our drawing is step 1. Our ions, which is the hardest part, is step 2. Step 3, going down here because I'm out of room. Step 3, we're going to write our FU. If you were here Friday, that's our formula unit. It's the ratio of our sodium to chlorines. Well, it should match our ion step and our diagram step. So in other words, I had 1 sodium for every 1 chlorine. So really in your brain is thinking this: sodium 1, chlorine 1. Well, in science, just like math, we don't write those ones. They're imaginary. If I write the chemical, I obviously have 1. And so I've got 1 sodium to 1 chlorine in math. This would be a 1-to-1 ratio. To make everybody's octet stable, I needed 1 chlorine and 1 sodium. So this in the box is step 3, your formula unit. The rest of this I just think in my head. So this is basically what we just drew. You can see on this example all of the electrons are represented. So sodium's 1 went over and it hooked up with chlorine here. And so now chlorine has sodium's electron, and here's that third level. Now that third level's empty, so we don't really need it anymore. So when it goes away, you'll notice that on the second level, he's got his 8 valence electrons. But now they've formed charges because they've gained and lost electrons. This is how a salt formula unit sticks together. Remember, we can't call it a salt molecule, only covalent things are molecules. So this would be several sodium and chlorines stuck together. The smaller ones represent the sodiums because they lost electrons and got smaller. The big ones represent the chlorines because they gained electrons and got larger. And so we have several sodium and chlorines stuck together with their charges, forming bonds and sticking that whole thing together. And so what happens is, when it happens a whole bunch of times, we end up getting a salt crystal. So this is what a crystal looks like. It's really, really organized, patterned, and it's really pretty. So now you'll actually get this joke. Get it? A salt. A salt. Ha, ha, ha. Really, what should be happening is chlorine should be dragging sodium because chlorine's electronegativity is higher than sodium's, but we won't get into the technicalities of this. All right, let's try another example. Ready? Grab your pencil. So let's try another example. So write example 2 on your page. Let's try calcium and chlorine and see how the story changes. So we're going to draw calcium, Ca. The difference here is that calcium is in group 2 on the periodic table, so calcium is bringing 2 valence electrons compared to sodium's 1 just a moment ago. Then we're going to hook it up with chlorine again, Cl, and I use X's again. You can use whatever you want, stars, hearts, open circles, whatever's fast. You'll get really good at this. This is kind of fun. So we need to make everyone stable. Everyone, not just chlorine, but everyone. So check this out. Calcium's the metal, so he's going to give up his electron. Chlorine's the nonmetal, so he's going to take it. Chlorine says, "Thank you very much. Now I'm stable." When they get stable, you're going to tend to see brackets put around the negative guys with a -1, saying that, hey, the only reason I'm stable is because somebody gave me that electron. I wasn't stable when I started, but I'm stable now. The problem is calcium is not stable. Calcium doesn't have a stable octet. He has this 1 valence electron still sitting here. So what we're going to have to do is we're going to have to change up the ratio. It's not going to be a 1-to-1 ratio like sodium and chlorine. So he's got to give that electron up. So we have to draw another chlorine that's going to take that extra electron, and we're going to put it right here. So again, since he took it, we're going to give him a bracket and a -1. Well, now, is calcium stable? Lost 1, lost 2, so that means now he looks like argon. He has a stable noble gas configuration, and he has a +2 charge. So now for our ion step. So what we're going to do is we're going to say calcium lost 2 electrons because he gave up 2. Chlorine gained 1, then another chlorine gained 1. I'm totally okay with you writing it this way, but some people think that's repetitive, so look what we do. we combine those two chlorines and we say calcium lost 2. Chlorine gained 1, and he did that twice. So if you're going to write this in your notes, write down that 2 at the bottom means I did it twice. The -1 means I gained 1. So chlorine gained 1 twice. So what you're not going to do is you're not going to make this a -2. Chlorine did not gain 2. Altogether they did, but I only want to know what happened inside this first bracket. Chlorine gained 1, and he did it twice. So now when we do our FU step, we write there was 1 calcium for every 2 chlorines. So really your FU step is this step right here, but the top numbers go away. And whatever you're left with is what you have here. Or I think it's a little easier to go back and look at your picture. How many calciums did you draw? 1. How many chlorines did you have to draw? 1, 2. So that's what that 2 represents. I had to draw 1 calcium and 2 chlorines for everybody to be stable. Here's a little bit cleaner version if that helps you at all. Same thing. And then we would draw our Fu, which would be CaCl2. Okay, one more example, then I'm going to turn you loose and you get to try on the homework page that you should have grabbed on the way in. All right, here goes nothing. Example 3. We're going to do potassium and oxygen. So potassium is in group 1, so he's going to bring 1. Oxygen is in group 16, so he's going to bring 6. 1, 2, 3, 4, 5, 6. I like to spread them out. They're electrons. They don't like to be near each other. So potassium gives 1 up. Oxygen takes it. The problem is I've got an empty hole right here for oxygen. He needs another one. So I've got to draw another potassium with an electron that goes right in here for oxygen. So you just keep adding back and forth until everybody gives them up. So you're like, oh man, but I have one more. Well, then add another guy. And then you're like, oh, when I add another guy, well, then he doesn't have enough. Okay, well, then add another guy. So you just keep going back and forth until everybody's full. So our ion step here was potassium. What did he do? Lost 1. How many times did he do that? Twice. What did oxygen do? Oxygen gained 2. How many times did he do that? Once. So there's a little imaginary 1 down there, but we don't write it. It's imaginary. So our FU step is just K2O. And again, if you go back, matches your diagram. You had 2 potassiums and 1 oxygen in your picture. That's all, folks.